Welcome back. We are continuing with the remaining examples, the worked examples for now. So let's start with example 1. A drive system is used to take up a role in a paper making process. The paper is wound on a drum such that the radius from empty to full varies from 0.5 to 1.5. The drum is driven through a reduction gearbox, assumed 100% efficient, and the process requires such that the tension in the paper is maintained at 100 newtons and the paper velocity is 20 meters per second. Sketch the torque speed characteristic of the load as seen by the motor. Determine the required motor rating, power rating, and determine if a different drive is used which has field weakling and allows a maximum speed of 150% of the base speed. Okay. So let's get into it. Okay. So our assumptions first, we've been given two radii. The radius first one was 0. Okay, radius from 0.5 to 1.5. The radius was 0.5 meters. That's the first radius. And the second radius was given us 1.5 meters. We're also given the velocity as 20 meters per second and a constant load torque of, was that even the torque? It was the force as 100 newtons. Okay. So let's go. At R is equal to 0.5. At R equals 0.5, we have our torque. Torque is given by a force times the radius. So our torque will be 100 multiplied by our radius 0.5, which gives us 50 Newton meters. That's our load torque. Then the speed would be omega is V over R, which is 20 0.5, which is 40 radians per second. But we are supposed to sketch the characteristics as seen by the motor. So we have to calculate the torque on and speed on the motor side. So at Tm, or first our omega m. We're given the gear ratio as 4 is to 1. So this would be 4 times omega L. That gives us 4 by 40, which is 160 radians per second. the we know that since it is 100%, our efficiency is the load power over the motor power. If you are assuming 100% efficiency, then it means PM is equal to PL, and power is given by torque times speed, right? So this would be TL times omega L over omega M. Our load torque is 50 Newton meters. Omega L over omega M would be the inverse of the gear ratio, so that's 1 over 4. So we get this as 12.5 Newton meters. So now at R being equal to 1.5, we'll repeat the process. First, find the load torque. Is 100 by 1.5. This will be 150 Newton meters. Omega L would be V over R, which would be 20 over 1.5. And that gives 16.33 radians per second. We go back, want to find the motor speed. The same thing, but we multiply, so that will be omega L by 4. And that gives us 53.33 radians per second. And then our motor torque would be the load torque as we've seen divided by 4, and that gives us 37.5 Newton meters. So if you want to sketch the characteristics as seen by the motor, as this torque and this. So at the first point we had our torque to be 12.5 and our speed to be 160. The second torque was, let's say, 37.5 with speed of about 53.33. So our first point is somewhere here, and the second is here. So the motor supplies rated torque. So the torque characteristic should be almost linear. So something like this. These are the load torque characteristics as seen by the motor. Then the next is to calculate the rating of the motor. So for the rating of the motor, the rating will be given by the power times the speed. But in the first scenario, we are assuming field weakening is not possible. So if that's the case, the motor has to be able to supply this maximum torque at all speeds. So it has to supply this and continue supplying it even at this speed. So this would be where we get our rating. So our PM would be given by 37.5 multiplying 160. That will be 6,000 watts. Then okay. The second scenario says we should assume determine the rating if a different drive is used, which allows field weakling, and a maximum speed of 150% of the base speed. Okay, so if we are using a drive that allows field weakling, this 160 would be our maximum speed, right? And then we can calculate the base speed from that. Our base speed, if omega max equals 1.5 omega base, so omega base speed will be the maximum speed, which is 160 divided by 1.5, and that gives us 106.67 radians per second. Nice. Okay. And then so we've gotten our base speed, right? So in this case, the motor only has to supply the rated torque up to the base speed. Let's say that will be somewhere here. Then from that point onwards, if field weakening is allowed, it reduces and behaves this way. So in that case, we'll have a graph that looks something like this up to the base speed, then slowly up to this point, then it comes down. Alright. So in that case, the rating of the motor would be at this point, which will be given by a rated torque. The motor rating will then be a rated torque, which is 37.5 times the base speed, which is the 106.67, and we get it to be 4,000 watts. Let's move on to the next question. Number 2. The drive is employed in a hoist system that is used to raise and lower weights. Or this weight hangs on a cable that is wound on a drive. And maybe assume to have a constant weight. A drum is driven by a motor. So we have a motor, gearbox, and a drum from which the load is hanging. Okay. So for our diagram, we have the motor to a gearbox. So this motor to a gearbox, which is then connected to a drum from which the load hangs. So we have something like this. And we know this as 500 kilograms, right? Velocities of plus or minus 2 meters per second is raising, or it says velocity plus or minus 2 meters per second. Radius 0.5. Our radius is 0.5 meters. We've been given our motor speed as 1500 rpm. We are supposed to find the gearbox ratio. N is to 1. Okay. And so for any other information, with an efficiency of 0.85, So and our efficiency is 0.85, right? So for the first one, we are supposed to calculate the gearbox ratio, which will be given by omega m over omega L, right? So we can find this by V over R, which is 2 over 0.5. And this is 4 radians per second. And omega m 1500 multiplied by 2 pi over 60, which gives us 1500 multiplied by 2 pi over 60. This gives us 157.08 radians per second. So our gear ratio, would be omega m over omega L, or m is equal to this, which gives us 157.08 over 4. It gives us 39.27. But it says we should pick the nearest integer, so we are going to use 39. So our n becomes 39. And it says the torque and power provided by the motor when lifting the maximum weight. So when we are lifting the maximum weight, the motor is what will be generating power to lift the load, right? Torque and power provided to lift. So we know we have the efficiency. Now efficiency would be the input over the output. When we are lifting, the input is from the motor. So we have PM over PL. So our PM, oh, sorry, output over inputs. I always get confused. PL over PM. So our PM will be this divided by the efficiency. And we know our efficiency is power is given by torque times speed. So our motor torque will be this multiplied by the speed over the efficiency over this. So we already have, when lifting at maximum velocity, we've calculated the load. Have we calculated load torque? When lifting at maximum velocity, our load torque is given by um, 500, which is the weight, mass multiplied by the weight, 9.81. This gives us the, what's it called? That gives us the force. And then to get a torque, we multiply that by 0.5. So that will be our load torque divided by the efficiency 0.85. And our omega L over omega M, that will be the inverse of the gear ratio. So that's times 1 over 39. This gives us about 50. No, this gives us so times 0.5 divided by 0.5. That gives us 73.98 Newton meters. Then the second part says when it is lowering the load at the maximum velocity. I think when it's lowering the load, it's moving in this direction. Right? That's a negative 2 meters per second. Or it's still moving downwards 2 meters per second. But when it's lowering, it's the weight that is now driving the motor because this is falling on its own. So this is where the force is generated, and then that power is now being transferred to the motor. So the motor works as a generator in this case. So we have so in that case we have the in this case the efficiency would be the motor, since the motor is not the output, is PM over PL. And we have PM being equal to the efficiency times the load, right? That's TL CM times omega efficiency times TL times omega L. So TM is efficiency times TL times omega L over omega M. Okay, and that would be 0.85. The load torque, that's the weight multiplied by acceleration due to gravity, then multiplied by the radius. And we know this is the inverse of the gear ratio, right? But in this case, the speed is it the speed? Yeah, the speed is negative since it's moving in the opposite direction. So our load torque then becomes that gives us 53 negative 53.45 Newton meters. Let's check and see. Alright. So we'll end here for now.